Actually, physicists are biophysicists. It's like, I think about that.
Not even close.
All right, so for the energy level diagram, it's gonna look like this: sp2 with a p. They're gonna be two lone pairs and two bonds. When we do the bonds, again, just show one oxygen bonding in two places. So an sp2 coming here, bonding here, and a p coming here and bonding here. If you draw two separate oxygens, let's say if I drew this like this, an oxygen sp2 here and an oxygen p, it makes it look as if they're two separate oxygens. I think two oxygens bonding to this one oxygen. Okay, is that clear? So just draw one O with two orbitals bonding in. It's a double bond.
Are you recording?
Yes, it is recording. That's recording. All right, are we good with this?
Yeah. Well,
Okay.
when there were different atoms, then we would have to include like the hydrogen that you were showing that.
Yeah. All right, let's take a look at some more examples of multiple bonds here. Here. And see if you could visualize this. This is, do you know the name of this molecule here? Ethene. Ethene has a carbon-carbon double bond. Do you see what they're doing here? They're showing the sp2 orbitals in the plane, trigonal planar arrangement of sp2, and then the p's are perpendicular to the plane. And so here you could see this would be a pp pi bond. But I don't like this. I don't like them to label it here because it makes it look like they're two pi bonds rather than one pi bond. It's only one pi bond. And so one pi bond consists of overlap here and overlap here, so we have an electron cloud in both places. This is showing the electron cloud. Okay. That's a pi bond. Here you can see the sigma bonding. Do you see the sigma bonding? The sp2 sigma bonding in the plane. And so this is another representation of multiple bonds. This is a triple bond. This is acetylene, the one we did earlier. Can you see it here? This is sp sigma bond, and then we have the p orbitals in the plane here, right? In this plane. This is one pi bond again, one pi bond here, right? And then we have another plane that's perpendicular to this. This is the other pi bond here, in the plane perpendicular. Do you see that?
Yeah.
Okay. This is a molecule we did earlier. This is formaldehyde. What's the bond angle here? HH 120, right? A lot of people say 90. But here you can see this is a side view, kind of, where we put the p orbitals perpendicular to the plane. Here's the pi bond here.
Wait, why is it 120?
sp2 have that.
Oh, I guess it's
You see the HCH bond angle is up here, 120. Let's look at some more complicated molecules here. This is, you recognize this? This is missing lone pairs, but this is formic acid or methanoic acid. And so you can see this is sp2. This is sp3. And so up here we're going to have the carbon-oxygen bond is going to consist of sp2, sigma, sp2 sigma. Remember what Petrucci does. Petrucci doesn't hybridize. I hybridize. And so this is sp2 sigma. Right? Because what is the hybridization on oxygen? sp2. So we got the sp2 sigma and a p pi bond. Over here, this would be a sp2 sp3 sigma. Over here, this would be a sp3 s sigma. Do you guys see it? Yes? So we could draw it here. The carbon, sp2, sp2, sp2. We got the three sp2s. And then the oxygen, sp2, sp2, sp2. Two lone pairs on the oxygen. Right, so they're supposed to be here. And we got the sp2 sigma bond here. Let's go down. And a. Now how do I draw the pp pi bond? This is top view, right? So we got a pp pi bond here. And we got the sp2 sigma here. Okay, what's happening here? What's happening here is we got an sp2 s on hydrogen sigma. What's happening over here? We have an sp2 to sp3 sigma, and then we have two in the plane. This other sp3 is going to hydrogen's s. So this sp3s sigma to hydrogen, and then what's happening with the lone pairs? One lone pair is sticking out. And one lone pair is sticking in. And so do you see it? Can you visualize it when you look at that molecule? Can you visualize what's happening with the orbitals? Yeah? Good. What are the angles we expect? Less than 120? Actually, this is tricky. Take a look at the angles. Could you have guessed those? No. We would have just said greater than 120, greater than 120, less than 120, less than 109. We need to actually measure it on the structure.
Why is it one sec greater than 120?
This side, because it's double bond. It turns out it's less than 120.
I mean, like 124 degrees. Huh? Why is it?
Oh, I mean, sorry. Greater than 120, greater than 120, less than 120. That's what we'd have predicted because of the double bond. The double bond pushes these two in, so this one's less, these two are greater.
Oh, okay.
Actual experiment. This is why we don't want to be so precise sometimes. Actual experiment shows how the bond.
How do they measure molecular?
How do you measure the angles? Experimentally? There are different ways to measure it. Actually, numerous different ways to measure it. And so these can be measured based on the vibrations. It can be measured in freezing it into a solid and then measuring it using X-rays. This kind of stuff. Okay, what's the hybridization on this carbon? This is SP, this is SP. I don't know why he's not drawing the lone pairs. And so this triple bond is going to be an SP sigma and two pp pi's. Can you do the orbitals for this? Yeah, it's not that difficult. sp3, right? sp3, sp3, sp3. And so we got all these sp3s, and then hydrogen here, and a hydrogen here. right? sp3s. And then this carbon is going to be sp3 to nitrogen's sp. So we're going sp3 to sp, right? Sigma. Oops, carbon. Okay, and then this carbon is going sp to nitrogen's sp. So this is sp, sp, sigma. Now where's the p pi's? Yeah, one's, we'll do side, looking on profile. One's in the plane, pp, and the other is perpendicular out of the plane, coming out. This is the other one. And then where's the lone pair? The lone pair is in an sp orbital here. Do you see it?
So that's top and side view combined together?
Well, it's the top view for the blue, the side view for the green. We could twist it and make it top view for the green and side view for the blue, but it's going to look exactly the same, right? Okay? With that? All right. What we've just been talking about is something called valence bond theory. Valence bond theory is the quantum mechanics light version. Valence bond theory is quantum mechanics light because it's easy. We could do that. Did you see we just did those big molecules pretty quickly, looking at the orbitals? Molecular orbital theory is the quantum mechanics full version. So what's the difference between the light and the full version? Well, some of the features of the full version are missing in the light version. And sometimes the light version doesn't give us accurate answers. And so what are we missing in the light version? We're missing, you know, the energies. You know, no spectra. That is, we can't, you know, we can't predict, you know, what kind of transitions we're going to do. If we excite this electron to a higher energy orbital, you know, that kind of stuff. One of the other problems with the light version is sometimes we get the wrong answer. Sometimes. We don't have this problem with the full version. The full version will get the electron density. We'll get the excited states. Therefore, we can get the spectra. You know, how it interacts with light. We get the, etc. So why do we use the light version? Well, why would you use the light version? You usually use the light version because it's cheaper or it's easier, right? Simplified, right? Rather than the full version. Maybe the full version has too many features, too complicated.
We don't need, for example.
And so it's both. It's cheaper. Because do you need a computer to do the light version? No, we're just doing it in pencil and paper. For the full version, do you think you need a computer? Yeah, you're going to be doing calculations. For the light version, did we have to buy expensive software? No. For the full version, do you have to buy expensive software? Yes. But what are the limitations of the light version? Well, the biggest limitation of the light version comes with O2. You know, here's where the distinction. Quantum mechanics light doesn't work for O2. And so let's write that over here.
For O2.
Fails for O2.
Didn't we just do that?
Yeah, we just did it.
It's wrong?
It's wrong. But not that, you know, even though it's wrong, it's how far off is it? Now, let me talk about O2. This is the okay. They don't have it here. Let me just look it up here. Is the phone working? Let's just pick the first video I saw. Volume's not working.
No?
All right, basically, we could have liquefied oxygen, liquid oxygen. Liquid oxygen is very dangerous, though. You got to be careful with liquid oxygen. He might have both, liquid oxygen and liquid nitrogen. This is just a magnet here. So, a lot of dialogue. All right, now this is liquid nitrogen here. Liquid nitrogen and then oxygen gas, passing the oxygen gas through here. It was the oxygen gas. When a gas expands, what happens?
Pressure.
The system does energy. As the system does energy, actually temperature will drop because the energy comes from somewhere surrounding. And so as it passes through here, it cools down the oxygen gas and you can liquefy it over here. So it's capturing liquid oxygen. Liquid oxygen is always very scary because liquid oxygen is a very powerful oxidizer. So you got to be careful. You don't want any organic material here. Because organic materials like wax or whatever will ignite. Yeah. And we've had lots of liquid oxygen explosions everywhere.
Is it safe to breathe there?
No, it's so cold. It's like if you, I don't know if you played with liquid nitrogen before, but it easily causes frostbite.
So what is he doing right now? What is he doing?
Look at the gloves he's wearing. Also, if it splashes on you, I've splashed liquid nitrogen all over my arms, and it hurts.
So
What's he doing? That's liquid nitrogen. Did liquid nitrogen, you see, did it interact with the magnetic field? No. Well, watch liquid oxygen.
Oh.
Liquid oxygen is captured by the magnetic field there.
That is so cool.
Isn't that cool? This is liquid.
What? Why would it do that?
Why would it do that? Because liquid oxygen is paramagnetic, whereas nitrogen is diamagnetic. And so that's the oxygen trapped in the magnet.
Paramagnetic is when it's excited, right? Excited state.
It's ground state.
Diamagnetic.
Yeah. Diamagnetic. So let's talk about paramagnetic and diamagnetic. This is the reason why we know valence bond doesn't work for oxygen, because valence bond gives us the wrong answer. So
So why would it hurt when the nitrogen liquid touches your skin?
Oh, it's so cold. It's a strong magnet.
In order for it to be a liquid, it has to be very low temperature. Is that why?
Yes. Very low. All right, let's take a look at oxygen. Oxygen is expected to be paramagnetic or diamagnetic, and what's the difference? Oxygen is expected to be diamagnetic because all the electrons are paired. All electrons paired. Therefore, diamagnetic. Diamagnetic means it's no attraction to magnetic field. In fact, it's going to be weakly repelled by magnetic fields. But the fact is O2 is paramagnetic.
Wait, so it's diamagnetic?
Paramagnetic. It's experimental fact. And so something's wrong with our theoretical understanding. In fact, something's wrong with valence bond theory. You remember Bohr theory?
Yeah.
Something was wrong with Bohr theory, so what did they do? They dumped it into the waste bin, basically, of old theories. And so Bohr theory was completely abandoned, but we don't completely abandon valence bond theory. Do you know why? It works for pretty much most things. It gives you the electron density cloud, but sometimes it's off a little. You know, it's always going to be off a little, but it's going to be close, right? And so what we have to do is we must use the full version. What was the full version called? Must use MO theory, or molecular orbital theory.
So we need a computer?
We need a computer for more complicated ones. For simple ones, we don't necessarily need a computer for. And so what we're going to do is, this is more complex. More complex. Therefore, we're going to limit ourselves to diatomics. To diatomic, simple diatomic molecules. If we just do diatomics and nothing more complicated, then it's manageable.
We can use the full version.
Yeah, we're going to use the full. We aren't going to do the calculations to calculate the energies. There we'd need a computer to calculate the energies. But we're going to, you know, we could do some, not everything.
Diatomic.
Okay. All right. So what's the difference? The difference is, in valence bond, if you have a hydrogen S and a hydrogen S, you overlap the orbitals, right? You form a SS sigma bond. In MO theory, what they do is they take the hydrogen S and a hydrogen S and then mix those completely. Mix them like hybrid orbitals. In hybrid orbitals, do you remember mixing the orbitals? But the orbitals were on the same atom. In this case, we're going to mix orbitals from two different atoms. And so we're going to take the S orbital from atom A and the s orbital from atom B, mix them together, and do you know what we're going to get? We're going to get new orbitals. But those new orbitals are going to be called molecular orbitals, not atomic orbitals. And so the difference is we generate an orbital, a molecular orbital, that this is one orbital that spans the entire molecule. And so we don't have atomic orbitals now, we have molecular orbitals now. And so if we take an s orbital, we generate new. Actually, there's two ways of adding it. We can add it like this, or we can add it like this, depending on the phase, right, or how you flip it. And so there's this additive and subtractive additions here. And so in other words, when we take two atomic orbitals, we get two new orbitals. These new orbitals are called molecular orbitals. And the molecular orbitals form from the atomic orbitals. And so let's go on to the next figure here in your book. And so this is showing it here in terms of energy. We have this constructive addition here, the adding here. This forms a molecular orbital. It's big. You know, this is just one orbital, not two orbitals. This one orbital spans both atoms here, and it spans the entire molecule. And so this is going to concentrate electron density in this region here. That's one. Or the subtractive addition here. The subtractive addition, we have a node here. And so there's no electron density, or very little electron density, between the two nuclei. And so the two nuclei are going to see each other and repel. And so this one's called anti-bonding, this one's called bonding. And so what we do is we take these two atomic orbitals and form new orbitals. New orbitals are called the sigma 1s bonding orbital and the sigma 1s star anti-bonding. The sigma is because the orbital encloses the internuclear axis. Okay, this sigma is in a way similar to valence bond sigma. In a way it's different because this sigma actually represents the orbital. Rather than calling it an s orbital, we call it a sigma orbital. Okay. The 1s subscript just tells us where that molecular orbital came from. It came from taking 1s orbitals, mixing those. Okay. This is what it looks like in terms of probability density here. And so we just get an electron cloud. Oops. And so if I look at the 95% probability boundaries, it looks like that. But basically, the sigma 1s orbital is just like this, electron cloud here. And the sigma star 1s looks like this, electron cloud here, but a node between the two. That's it. So let's start doing this for molecules here. For molecules, let's look at hydrogen, for example. If we look at hydrogen, we take a hydrogen 1s orbital here with one electron, a hydrogen 1s orbital here with one electron. We bring these two 1s orbitals together. And so here we got this, we got this. When we bring them together, they mix both constructively like this and destructively like this. And so this one, this is called sigma 1s, this one's called sigma star 1s. And what they look like is this. This is sigma 1s, cigar shape. This is a sigma star 1s. We got the cloud there. Now, what we do with the molecular orbitals is we just fill them. So we'll just fill them like that. There are two electrons, max capacity. So Pauli's exclusion principle, Pauli's, exclusion, excuse me. What was Pauli's called again?
Exclusion principle.
Yeah, Pauli's exclusion principle still holds. That no two electrons can have the same set of four quantum numbers. But we aren't going to generate quantum numbers for the MO. And so what does hydrogen look like in MO theory? MO just stands for molecular orbital theory. In terms of MO, we have a hydrogen here, and then we got two electrons in the sigma 1s orbital. In terms of valence bond theory, it looks like this. We've got two electrons here. And so this is a 1s, this is a 1s, this is a sigma 1s. That sigma 1s has a capacity of 2. Now the next higher energy orbital is empty here. The next higher energy orbital would be the sigma star 1s. The next higher energy orbital here would be the 2s orbital and the 2s orbital here. Right? And so this is what we have to do. For diatomics, actually, we'll do some other ones. Let's do some other examples here. We can do some exotic species. For example, let's do hydrogen with an H plus here to try to form H2 with a plus charge. Will H2 with a plus charge work? Yes or no? In other words, in MO, can I have just one electron in the sigma 1s orbital? Just one electron. In valence bond, this would be equivalent to trying to overlap a 1s here with one electron with an empty 1s orbital here. Does it work? Actually, in valence bond, it actually does work, because here you're going to have less electron density, but you still have some electron density in the internuclear region. This bond is going to be much weaker, right, in this bond. And so, does it work? Well, we have something called bond order. Bond order is equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. Now, what is a bond in MO theory? A bond in MO theory equals more bonding electron density versus anti-bonding electron density. And so in this case, it turns out that the bond order, BO, is 1/2. We got one electron. So it's like a half a bond. And so it should be weak. Versus hydrogen, the bond order would be 1. It's like a single bond. Okay, let's go on to another exotic species. What about H2 minus? What if I add an electron to a hydrogen molecule? Let's look at valence bond. So valence bond, this would be similar to taking a hydride with 2 electrons, hydride, and trying to bond it with a hydrogen with 1 electron. And so if I take a hydride and bond it to a hydrogen, will it work? Will it work? No. Hydride bonding to a hydrogen. No, this doesn't work, right? There's 3 electrons. Do you see it's not going to work?
So we said 3 electrons versus being 2.
Yeah, this is, and this orbital is already full. How can you overlap with an already full orbital? Throw in another electron there. Is it going to work? No.
So it only works for diatomics and
No, this is for valence bond.
valence.
Right? And so the H2 minus. How about an MO? And so let's look at MO theory for this. In MO theory, we just start memorizing a new set of orbitals. We have the sigma 1s followed by the sigma star 1s. The sigma 1s looks like this, the sigma star 1s looks like this. And now if I have H2 minus, I have 3 electrons. Valence, 1, 2, 3. And so that means I have 2 electrons here and 1 electron here. But in MO theory, a bond is having more bonding electron cloud than anti-bonding electron cloud. And that's the case here. I have more bonding density than anti-bonding density. And we can see, if we look at the bond order is 2 minus 1 divided by 2, which is 1/2. And so MO predicts that we should be able to form H2 minus, right? But it's going to have a weak bond. Experiment predicts, well, actually experiment shows that H2 minus exists. And so MO's correct here. Valence bond predicts you can't form it because this orbital is already full. Does that make sense? What about adding one more electron, H2 minus? If I try to add one more electron to this, then I get 4 electrons, and I fill this up, I completely fill my antibonding. And so what happens now is that the antibonding cancels the bonding, and the bond order comes out to 0. And so that means H2 minus doesn't exist. And let's observe. You can't form it.
So why would oxygen fail on the other one?
It's just because it's not accurate. Oxygen failed valence bond because valence bond is not 100% accurate. All right, now that's the first period. Let's go to the second period. And so let's take a look at the second period.
This sigma star 1s is higher energy than sigma 1s.
Yes. All right, when we go to the second period, now we got to look at some p orbitals and how the p orbitals add. And so what we do is, this is called LCAO. This is called a linear combination of atomic orbitals. When we do the LCAO, this is what we'll do. We'll do it in phase. Do you see this in phase? This is constructive. This is called the sigma 2p. But if we do it this, we got to do it out of phase too. There are 2 ways to add these orbitals. When we do it out of phase, it's destructive. And so we call this the sigma 2p. We call this one the sigma star 2p. The in, the out. Do you see that? The sigma star is going to be antibonding. It has a node here. That's a sigma type addition. What about a pi type addition? So rather than putting the p orbitals head on, you put them side on. In phase, do you see this? This is a pi 2p. It looks like just like a pp pi bond, doesn't it? But this is just one orbital, not 2 orbitals. And then we do it out of phase. Do you see this? It looks like 2 p orbitals are repelling each other. But this is just one orbital. This is a pi star 2p. And so we have the bonding, the antibonding. Let's continue here. So when we combine the p's, we have the px's. The px's form the sigma 2p, the sigma star 2p. We have the py's. The py's are going to come side on. That's going to make the pi 2p's and the pi star 2p's. And then we have the pz's. The pz's come side on. And so they're just like the py's, but in the plane. These are perpendicular to the plane. And so we have the bonding and the antibonding here. So we generate what's called a MO diagram. In terms of energy here, this is for fluorine, by the way. In terms of energy, the sigma 2s should be the lowest in energy. The 2s orbitals are lower. And so then we generate the sigma star 2s. We'll talk about where that energy goes. And then the sigma 2p should be lower in energy than the pi 2p's, are more stable. And so we generate a diagram that looks like this. We actually have 2 diagrams. So let's talk about these 2. These are called MO diagrams. The top MO diagrams are kind of what we expect here. What does this 2s orbital look like? Round. What does a 2s orbital look like on it? Round. And so sigma 2s is going to look like a cigar. Right? The sigma star 2s looks like two orbitals repelling each other, like this. Now, which one is better, a sigma or pi type? Sigma. And so if we look at a p like this and a p like this, we bring those two p's head on, we're going to get this one, the sigma 2pz. But we also generate the sigma star. The sigma star is when there's no. Now, this conservation of energy, so if this one drops down this much energy, this one has to pop up the same amount. You see that? Okay, that is head on. Now we bring them side on. So this is one here, this is one here. And so we generate one of these sets here. This is the pi 2p. This is the pi star 2p. And so here we got the two cigar shapes. It's like a pp pi. This is where they're repelling each other with a node there. And then we have this one that comes out, one goes in. Okay, then this one comes out, one goes in. And so we're going to have one lobe that comes out and one lobe that goes in. Looks exactly like this, it's just tilted. And then this one comes out, goes in, comes out, goes in. Okay? And so this is how we map it out. If we have a diatomic molecule AB, what are the orbitals? Well, if we had a atom, what are the orbitals? The orbitals, s orbital, 1s, 2s orbital. What's next? 2p orbital. 2p, 2p, we have three of them. 2p. Oops. That's three, right? Then what comes next? 3s. And then what? 3p. You see, we build up all the orbitals, and we just memorized them. How did you know these orbitals? You memorized them, right?
Yeah.
Now you have to do the same thing. If we have a diatomic molecule, AB, what's the first orbital? Well, let's go with second period to keep it. Second period, we'll just look at the valence only. And so the first orbital is going to be the sigma 2s. After the sigma 2s comes the sigma 2s star, yeah, is out there. It's up there in energy. But the next energy after, yeah, sigma 2s star. Let's do that. Sigma 2s star. Then what?
2p.
Then the sigma 2p. The sigma 2p looks like this. Sigma 2p. And then what?
The sigma 2p star.
Well, sigma 2p star actually is way up there in energy. The next one is pi 2p. Okay. The pi 2p comes next. But take a look at one thing. Do you see the electron cloud for the sigma 2p? And the electron cloud for the sigma 2p and the sigma 2s? The electron clouds are kind of in the same volume of space. Do you see that? Same volume of space. And so this is a weird thing that happens. Which one do you expect to well, I Actually, let me stop here for a second, talk about this, and then we'll go on. There are two diagrams here. And the two diagrams differ based on what's happening here with this. Do you see the sigma 2p here? The sigma 2p in the second diagram gets popped up here. This is the sigma 2p here. And it depends on z. What's happening with z? If z is high, then we have the normal diagram. But if z is less than 8, then something happens with the sigma 2p here. And so this is what's happening. What's happening when z is greater than 8, what it does is which one's more penetrating, a 2s or a 2p? 2s is more penetrating. And so when z is high, the 2s is more the 2s gets pulled in tight to the nucleus. This is sigma 2f. And then the 2p are less penetrating, right? And so the 2p don't get pulled in as tight. This is the 2p, sigma 2p. However, when z is less than 8, then what happens is we have less nuclear charge, and so it doesn't pull in the orbitals as tightly. And so when z is less than 8, there's less of an attraction for the electrons, and so the orbital doesn't contract as much. And the same holds true for the sigma 2p. And so when z is less than 8, we get what's called electron-electron repulsions between the 2s, sigma 2s, and sigma 2p. Electron-electron repulsions. Here, the electron repulsions are less significant because there's more separate space. Here, they share the same space. And so the reason why this happens is because of electron-electron repulsions. The sigma 2p pops up in terms of energy. All right, so finally, this is what we're going to do.
So for this section, what do we have to know? What do we have to know? Like to draw the...
Yeah, you have to know to draw them, and then you have to know these two separate diagrams. And so for this section, there's some memorization involved. And so let's go back to O2. What is Z for O2? Less than 8?
Equal to.
Equal to 8. Z equals 8?
Yes.
And so which diagram do we use?
The one that is...
We use this diagram here. And so the diagram, you have to memorize the order. Sigma 2s, sigma star 2s, sigma 2p, and then the 2 pi 2p's, and then the pi star 2p's, and then the sigma star 2p. And then O2 has how many valence electrons total? 6 and 6 is
so
12 electrons. And so we fill them. 1, 2, 3, 4, 5, 6, 7, 8. These pies we fill one at a time. 9, 10, 11, 12. And so when we look at it, is O2 paramagnetic or diamagnetic? Paramagnetic. And so this would be the MO diagram. And now let's draw the orbitals for O2. So we have an oxygen here and an oxygen here. What's the first orbital? Sigma 2s. Sigma 2s has 2 electrons. Okay, what's the next orbital? Sigma star 2s. Sigma star 2s has 2 electrons. We got electron density here. Okay, what's the next orbital? Okay, sigma 2p. Is sigma 2p and sigma 2s messing with each other? Not as much, because the sigma 2s are being pulled in tighter than the sigma 2p. They're more penetrating. So the sigma 2p can avoid the sigma 2s, so we don't have this pop-up here. And how many electrons do we have here? 2 electrons. And then what comes next? The pi 2p's. Okay, now we have a pi 2p above here and below. This is a pi 2p. It has 2 electrons in it. And then we have another pi 2p. Where's the other pi 2p located? The other pi 2p is located coming out of the plane and going into the plane. This has 2 electrons in it. And then what? The pi star 2p. Okay, one of the pi star 2p's, I'm running out of colors, looks like this. This is pi star 2p. It has 1 electron in it. And then there's one more pi star 2p. Where's the last pi star 2p? It's coming out.
This is a very creative figure in the test.
So this is a pi star 2p. It has 1 electron in. And this one.
Insane. How can you create this? Like, how can you create a problem?
So let's go ahead and do the electron density map. Okay, we're going to do the electron density here. The sigma 2s electron density is here. So this is sigma 2s, right? Okay, that's bonding or anti-bonding? Bonding. Okay, the next one is the sigma star 2s, which is anti-bonding. Here. Okay, the next one is sigma 2p, which is, should I try a different color for this? Yeah? So here's the sigma 2p, which is bonding, and then the pi 2p's. Wow. Okay, 1 pi 2p is up here, and 1 pi 2p is coming out of the board.
All right.
All right, up to this point, all the electrons are paired. Where do they come unpaired? In the pi star 2p. And so here there's going to be an unpaired electron here in the pi star 2p that's in the plane. And there's going to be 1 electron here in the pi star 2p that's
Is this even real?
coming out of the plane. Like that.
Wait, so are we going to have that? Like, do we have to do that? It's like, no.
Do you have to do that? No.
What do we have to do on the test?
What do you have to do on the test?
How are you doing that? Like, I'm just wondering, like,
No.
how precise do we have to be? Like,
Do you have to do this? Do you have to be able to do this? Yes. But this is so easy. What's so hard about it?
No.
Are you serious?
How can you say it?
When he say that, I can see.
Why is it so easy?
This guy.
Can we just do oxygen in the test? How can you grade something?
Okay, if you take a look at this, you know, what is this? A pi 2p orbital. We have 2 electrons in it. There. And this is a sigma star 2p orbital. How many electrons do we have in there? 1. And so you just go orbital by orbital, and it's not hard. You put them all together, then it looks hard, right? But if you just do it orbital by orbital, it's not difficult. And so let's take a look at fluorine.
It's gonna be more complex.
It's complex because you don't know. You haven't memorized the orbitals, have you?
No.
Let me do the same thing.
Up to what do we have to know? All that.
Basically, everything we've up to what orbital have you memorized for atoms? Let's say I had a nitrogen atom here. If I have a nitrogen atom, then what's the first orbital? Let's just do the valence orbitals. If I do the valence orbitals on nitrogen, what's the first valence orbital on nitrogen? 2s. How many electrons do we have in there? 2. Is that hard? No. Okay, what's next? 2p. How many electrons do we have in the 2p? One of the 2p's.
1.
Actually 2 in 1. And then we have how many more 2p's? Altogether, how many 2p orbitals do we have? 3 of them, right? There's 1. Here's 2. That only has 1 electron, because nitrogen has 5 valence electrons. And where's the in and out of the board? So 1 orbital lobe sticks in, 1 orbital lobe sticks out, and that has 1 electron. Now you look at that, and it's the same thing. Do you see? Deconvoluted, it's easy, but when you convolute everything, it's hard. But can you see it if you went through step by step? Yes or no? Yeah? But when everything is overlapping on top of each other, it looks like a complete mess. But for the people who know what each component is, it's not a mess. They can pick through it and sort it out.
So this is color coded, yes.
And so, yeah, color coding helps for sure. And then when you look at the electron density map, you know, we have 2s electron density here. That's what we call the 2s. It's this sphere here. And then we have 2p electron density here. That's the green 2p. And then we have 2p electron density here, but it's only 1 electron's worth. That's the red here. And then we have this blue electron density here that comes out. And can you visualize it? Or try to?
I'm trying.
Yeah. What happens is it takes time because you got to learn the orbitals here and then do it. But basically what we see is this. When you look at the electron density maps of valence bond versus atomic orbital, they're very similar. You know, it's just what's happening with these. It's just what's happening with these. Here. And so we'll talk about oxygen a little bit more later, but we're going to stop here, and then we're going to go into the computer lab, and we're going to look at some of these. Okay.